Hi everyone! In the previous section, we have introduced the concept of a contracting map. Despite its significance in the theory of fixed-point iteration, it might be useful to introduce a few of its variants at this stage. A careful comparison of the similarities and the differences among these concepts will help reveal the subtleties underlying a fixed-point iteration. To start with, let us first define a subcontracting map. Similar to a contracting map, this is also a function from the closed interval AB into itself. It satisfies that for any given distinct points x and y, the distance between their images is strictly less than the distance between themselves. In other words, under a subcontracting map, the distance between 2 points will decrease. This is similar to the case of a contracting map. However, unlike the case of a contracting map, where the reduction is bounded by a uniform scaling factor represented by lambda, here, for a subcontracting map, we only know the distance is reduced. In some places, the reduction might be dramatic, while in other places, the reduction might be so small that it's almost imperceptible. Actually, if you consider the ratio of the distance between the images and the distance between the original points, then for a contracting map, this ratio is bounded from above by lambda. And since lambda is a constant that is less than 1, you can see that this ratio is not only less than 1, it is actually isolated away from 1 by some buffer area, which is the distance between lambda and 1. Yet for a subcontracting map, we might have unfortunately lost this buffer area. As x and y are varying in the domain, this ratio could approach 1 as much as we want. As you can imagine, such a loss of buffer area can probably be a source of difficulty for our mathematical analysis. Next, if we would like to relax our condition a little bit further, replacing the strict inequality by the slack inequality, then we get the so-called non-expansive map. Under such a function, the distance between the images of 2 points is less than or equal to the distance between the original points. The distance between 2 points may or may not shrink, but in any case, it is not going to expand. The hierarchy of these concepts is easy to see. Actually, if a function is contracting, then naturally it is subcontracting, which is in turn non-expansive. As long as a function is non-expansive, it is Lipschitz continuous, which of course is continuous. Hence, no matter if a function is contracting, subcontracting, non-expansive, given any of these conditions, we know it is at least continuous. Yet the inclusivity of each layer is strict. For example, consider the identity function from the closed interval 0,1 into itself. This function is clearly non-expansive, however, it is clearly not subcontracting. For a function that is subcontracting but not contracting, let us consider the function g from 0,1 to 0,1 given by gx is equal to x squared over 2. By definition, given any distinct points x and y in this interval, we see that the absolute value of gx minus gy is equal to the absolute value of x squared over 2 minus y squared over 2, which is equal to 1 over 2 times x plus y times the absolute value of x minus y. Now, notice that x is less than or equal to 1, so is y. Hence, if x and y are not identical, they can't be both equal to 1. In other words, x plus y over 2 will be strictly less than 1, which justifies that this function is indeed subcontracting. However, no matter which lambda we pick, as long as lambda is greater than or equal to 0 and is strictly less than 1, if we choose x to be lambda and y to be lambda plus 1 over 2, then clearly x and y are not equal to each other. Moreover, both of them are in the interval 0,1. It turns out that 1 over 2 x plus y is equal to 1 over 2 times lambda plus 1 over 2, which is greater than lambda. In other words, no lambda can be a contracting factor for g. Thus, gx is not a contracting map. Finally, recall that if the function is differentiable, we can often determine whether it is a contracting map by studying its derivatives. This is still true for subcontracting and non-expansive map. As always, let us assume that f is continuous in the closed interval AB and differentiable in the open interval AB. Now, the criteria is the following. If in the whole open interval the absolute value of the derivative is less than 1, then we know the given function is subcontracting. If the absolute value of the derivative is less than or equal to 1, then we know the given function is non-expansive. To see how these criteria work, let us look at the previous two examples. For the identity function, the derivative is equal to 1 constantly. As a result, this function is non-expansive. On the other hand, the derivative of x squared over 2 is equal to x. As we can see, as x is varying between 0 and 1, the absolute value of the derivative is always strictly less than 1. Hence, we conclude that the function g is subcontracting. Moreover, as x moves arbitrarily close to 1, the absolute value of the derivative can also approach 1 as much as we want. This indicates that there's no chance this function can become contracting. In other words, subcontracting is the best that we can expect. Now, hopefully, you have seen how these concepts are closely related to each other. In the next few sections, we will see how such tiny differences among these concepts can actually generate some subtleties for the fixed point iteration.